All right, for this example, we're going to look at the magnetic field flux in a solenoid. So a solenoid is a device, basically a coil of wire that produces a uniform magnetic field. And the way it does that is we stack a whole bunch of coils on top of each other. So these are all carrying current, and they all have the same radius. So here's our solenoid, and I'm stretching things out. In reality, solenoids are really tightly wound, and they look just like a big stack of. Let me redraw that. That was not a great magnetic field line. So this magnetic field line is essentially perpendicular, or in the same direction as the area vector for our loop. And it's a uniform magnetic field that points, in this case, from left to right. And so our magnetic field flux, well, we want to look at the integral of B, our magnetic field, dotted into a little piece of area. In this case, those two are pointing in the same direction. And so the dot product just yields a B times dA. And our magnetic field is uniform, so we'll factor that out front. And we just need to calculate the area of our circle. In this case, it's just B times A. We saw, and you can see this in the notes, that B, the magnitude of the magnetic field produced by a solenoid, is mu naught times N, which is the number of turns per unit length, times the current that it's carrying. A is just going to be pi times r squared here, where r is the radius of each little coil. And so our flux is pretty straightforward. We're just going to take the product of these two. And so this is going to be mu naught N times I times pi r squared. And we are done. So the thing to remember is, if you can get this situation where your dot product, where these two vectors are pointing in the same direction, dot product just becomes the product of those two magnitudes. And especially if the magnetic field is constant over your area, this becomes a pretty straightforward calculation, which is why it's useful to calculate these fluxes.